Before we get into definitions or concepts, I want to do something slightly different. Instead of starting with theory like we usually do, today we are going to start with a real system that you already use and we are going to break it down sequentially. Because once you understand that, everything else in AI will start to make sense. Okay, let's begin with something very simple. Open Google Maps on your phone, enter a destination. It tells you you'll reach in 32 minutes or 40 minutes, something. Now, pause for a second. That number looks precise and it is confident. But think about what it's actually doing. It is making a prediction about the future, not just based on distance, but it is also considering factors like traffic that is constantly changing, signals that don't follow fixed timing, drivers who behave unpredictably, and lastly, conditions that may shift minute by minute. So, the real question is not what it shows you, but the real question is how does it arrive at that exact prediction? One thing is obvious for us, it is not using fixed rules because fixed rules won't work for dynamic systems like this. So, there is no rule inside the system that says if this road, then 30 minutes. That would break instantly because the real world doesn't follow stable rules. It changes continuously. Instead, the system is trained on data, massive amounts of data. Every day, billions of devices send signals like location updates, speed, route choices, time taken for each segment. And over time, the system starts learning patterns such as how traffic builds at specific times, how delays propagate through connected roads, and which routes become unreliable under certain conditions. Now, here is the key shift. When you request a route, the system is not calculating in the traditional sense. It is evaluating, given everything I have seen before, what is the most likely outcome right now. That is fundamentally different way of solving a problem, not by writing instructions but by learning from examples. And this leads us to a precise way to think about AI. AI is a system that learns patterns from data and uses those patterns to make predictions on new situations. There are two important implications here. First, the system does not understand traffic the way a human does. It does not know why a road is congested. It only knows that certain patterns tend to lead to certain outcomes. Second, its strength comes from the scale. A human might observe traffic over days or weeks, but the system learns from millions of journeys across many cities and across multiple variations of time. That scale is what makes the prediction actually useful. Now, keep this in mind because this idea will repeat throughout the course. Whenever you see an AI system, it is doing some version of this. It has seen a large number of examples, it has extracted patterns from them, and it is using those patterns to predict what comes next. Now, with that understanding in place, let's step back and look at what this course is actually about. Foundations of AI. From curious minds to informed thinkers. This is not just a title, it describes a transition. Most people today interact with systems like Google Maps and stop at the surface. They see the output, they trust the result, but they don't examine the mechanism behind it. Curiosity gets you to ask, how does this work? But that's not enough because without a clear model, it's easy to overestimate what AI can do or misunderstand where it actually fails. This course is about moving beyond that, from curiosity to clarity, from using AI to understanding its behavior. Now, look at the line. AI is already shaping your world. This is how it works. This line connects directly to what we just discussed. When Google Maps suggests a route, it doesn't just inform you, it actually influences your decision. And when millions of people follow similar recommendations, it starts shaping real world outcomes. Traffic patterns, travel times, even the congestion itself. And that's the important shift. AI is not something separate from your life, it is already embedded in systems that guide your decisions, often without you noticing. So, as we move forward, I want you to adopt a simple habit. Whenever you encounter an AI system, ask what data is it learning from, what pattern is it extracting, and what exactly is it predicting. If you can answer those three questions, you are no longer just using AI, you are starting to understand it. So now that we have seen a real system like Google Maps, let's compress everything we discussed into one clear idea. Now, before we go deeper into how these systems are built, let's pause and connect this to something you already understand. I'm not talking about the technology, I'm talking about your own experience. Think about how you learned something physical. For example, riding a bicycle. Nobody gave you a rule book. No one said, turn the handle by exactly this angle, shift your weight by this amount. Instead, what happened? You tried, you lost balance, you fell a couple of times, you adjusted, and you tried again. Each attempt gave you a feedback, not in words, but in experience. And over time, something changed. You stopped thinking about it. Your body just knew what to do. Now, look at that process carefully. You did not learn from rules, you learned from repeated examples. And from those examples, patterns emerged. Now, let's connect this to AI again. AI learns in a very similar way. There is no fixed rulebook, and instead of instructions, you give it data, thousands or millions of examples. At first, it gets things wrong, just like you did, but each mistake gives feedback, and the system adjusts slightly and every approach, and then it tries again. Over time, the patterns begin to form, not because someone programmed them, but because they exist in the data. And as this process repeats, the system improves. Now, here is the important distinction. The process is similar, but the scale is completely different. You might have needed dozens of attempts or maybe hundreds to learn a bicycle. For an AI system, it learns from thousands or millions or sometimes billions of examples. That scale is what makes the difference. Now, we can define this clearly. Machine learning, in simple terms, is teaching a system by showing it examples instead of writing fixed rules. And this connects everything we have seen so far. Face Unlocked learn from many face examples. Maps learn from many journeys. Autocorrect learn from many sentences. The recommendations learn from many user behaviors. Different systems, same learning process. So, going forward, whenever you hear machine learning, don't think of it as something abstract. Think of it as a system learning the way you did through repeated experience but at a much larger scale. What is AI in one sentence? And here is the definition. AI is a computer system that learns from examples and experiences to make decisions or predictions. And it does this without being explicitly programmed with rules. Okay, now that sounds straightforward, but almost every word in that sentence matters. So instead of moving on, let's break it down properly. First part, learns from examples. This is the most important shift. Traditional software works like this. You write rules and the system follows them. But with AI, you don't start with rules, you start with data. Let's go back to the maps example and make this precise. Instead of telling the system if traffic is high, add 10 minutes. If peak hour, avoid this road. You actually show it. You show it millions of past journeys. You show it the actual travel times. Now, the system learns patterns like how delays form, how long they last, and how they affect the connected routes. So the rule is not written by a human, it is inferred from examples, and that is a fundamental shift. Now, the second part makes predictions or decisions. This is what the system actually does after the learning process. When new data comes in, something it has never seen before, it doesn't panic. Instead, it compares it to the past patterns. In maps, that means you request a route right now, the system evaluates current signals, past patterns, and similar situations it has seen before. And then it predicts this route will most likely take 30 minutes. Notice something important here. It is not retrieving an answer, it is generating a prediction based on similarity to past data. And this applies everywhere. Face recognition, for example, the system is not memorizing your exact face. It learns patterns like distances between features, shapes, and structures. So, even if lighting changes or the angle changes, it can still say this matches the pattern of this person. Now, the third part gets better over time. This is where AI behaves very differently from traditional systems. In traditional software, if you want improvement, you rewrite the entire code. In AI, improvement comes from more data. Let's go back again to the maps example. As more people use it, more routes are recorded, more traffic patterns are observed, and more edge cases are captured. So the system refines its predictions, not because someone updated the rules, but because it has seen more examples. Now, if you step back, all three pieces connect. It learns from examples, it uses those patterns to make predictions, and it improves as it sees more data. And that leads to one important mental model. Whenever you see an AI system, you can break it down like this: what examples did it learn from? What pattern did it extract? And what prediction is it making? If you can answer those three questions, you understand the system at a much deeper level than most users. Now that we have defined AI clearly in one sentence, let's move forward and clear up something equally important. Because understanding what AI is only half the story. You also need to understand what it is not. So, till now, we have defined what AI is and what it is capable of. Now, we need to correct something just as important, because most mistakes that people make with AI don't come from not knowing what it is. They usually come from misunderstanding what AI is not. And if these misconceptions stay in your head, everything you learn after this will be slightly distorted. So, let's start with the very first one. AI is not a human brain. This is where most confusion begins. AI does not think. AI does not understand meaning, and AI does not have any intent. Now, let's go back to the maps example. When it predicts 32 minutes, it doesn't understand traffic. It has never experienced a traffic jam. It doesn't know what frustration is, and it doesn't reason about why congestion happens. It simply recognizes that this pattern of inputs has historically led to this outcome. So, when people say AI understands language or AI understands images, that's shorthand. What it actually does is map patterns in input to patterns in output, nothing more. Second, AI is not magic. Every output has a reason, even if you can't see it. Let's take a recommendation system. When it suggests a video or a product, it can feel almost uncanny. But underneath that, it's doing something very concrete, comparing your behavior to millions of others, identifying similar patterns between them, and predicting what people like you tend to engage with next. There's no intuition, no instinct, just large scale statistical matching. And third, AI is not always correct. And this is a critical one, because the system is designed to give an answer even when it is uncertain. Think about how it works. It has learned patterns from past data. So when it sees something new, it tries to match it to the closest pattern. But if the situation is rare or ambiguous, or if it is outside what it has seen before, it will still produce an answer, and that answer can sound confident even when it is completely wrong. And this is not a bug, it is a direct consequence of how the system works. Prediction does not guarantee correctness. Fourth, AI is not just robots. Most AI is not visible at all. You don't see it directly, but you experience its effects. Take email filtering for example. Every email you receive has already been evaluated: spam or not, priority or not, is it relevant or not. This decision was made before you ever saw it. No robot is involved here. It is just pattern recognition running in the background. And fifth, AI is not conscious. This is different from intelligence. Consciousness means awareness, experience, and a sense of self. AI has none of this. Even the most advanced systems generating human like text do not know they are doing it. They are not aware of the conversation, they are not aware of you, and they are not aware of themselves. They are processing input and generating output. That's it. Finally, AI is not one single thing. It's an umbrella, and under it, there are multiple layers: machine learning, deep learning, language models, and each of these are more specific than the last. So, when someone says AI, they are often referring to a broad category, not a single system. Now, if you step back, all of this connects to one idea. People tend to overestimate what AI is and misunderstand how it actually works. So, here is the key takeaway I want you to carry forward. AI is powerful, but its power comes from pattern recognition, scale, and the vast amounts of data, not from understanding, awareness, or intelligence in the human sense. If you keep the distinction clear, you'll avoid most of the common mistakes people make with AI. Now that this idea is clear, let's move forward and look at something more concrete, because the next step is realizing how often you're already interacting with these systems. We are going to make this very precise now, because up to this point we have been using the word data quite loosely. But now let's define it clearly. Data is simply examples or information that a system learns patterns from. But that definition becomes much more useful when you actually see what counts as data. Because data is not just numbers or tables, it shows up in many different forms. For example, let's start with photos and images are data. Think about faces used in face unlock, X-rays used in medical diagnosis, and satellite images used in mapping. Each image is an example, and across thousands or millions of such images, patterns begin to emerge. For instance, in medical scans, the system is not told this is what a disease looks like. Instead, it sees many labeled examples, and over time, it learns these kinds of visual patterns are associated with this condition. Now, let's move to text. Text is another major form of data. This includes articles, emails, books, conversations, reviews. Systems like autocorrect or language models learns from massive amounts of text. They don't understand language like humans do, but they learn patterns like which words tend to follow others, how sentences are structured, and how meaning is typically expressed. So when you type something, it predicts based on those learned patterns. And next, numbers. Numbers are one of the most traditional forms of data. Think about prices, temperatures, scores, sensor readings, etc. For example, in a pricing system, the model might learn patterns between demand, time, and user behavior and then predict the optimal price. Now, audio. Audio is also data. This includes voice recordings, music, the phone calls, and the podcast. Voice assistants, for example, learn from large datasets of spoken language. They identify patterns in sound waves, pronunciation, and speech structure. So, when you speak, the system maps that audio input to patterns it has already learned. And now, one of the most important categories, clicks and actions. This is behavioral data. What you do. For example, what you click, what you search, what you watch, and what you buy. This is the foundation of recommendation systems, because behavior reveals patterns much more clearly than stated preferences. If you repeatedly watch certain types of videos or skip others or spend more time on specific content, the system learns these patterns are associated with this kind of user behavior, and then it predicts what you're likely to do next. Finally, the ratings and labels. This is what gives meaning to the data. Examples: spam versus not spam, 1 to 5-star ratings, thumbs up or thumbs down. These labels act as signals. They tell the system this pattern corresponds to this outcome, and without labels, learning becomes much harder because the system has examples but no clear indication of what they represent. Now, step back and connect all of this. Different types of data: images, text, numbers, audio, behavior, and labels. But they all serve the same purpose. They provide examples from which patterns can be learned. And this leads to one of the most important ideas in AI. The quality of the data determines the quality of the system. If the data is biased, incomplete, or if it is inaccurate, then the patterns learned will reflect those, and the predictions will carry those same issues. So, AI is not just about algorithms, it is deeply dependent on the data it learns from. And once you understand that, you start evaluating systems differently. You won't just ask how good is the model, you also ask what kind of data shaped this model, because that's where the real behavior comes from. Since we understood how AI learns from data, now we need to organize everything we have discussed into a clear structure. Because right now, terms like AI, machine learning, and deep learning are often used interchangeably, and that creates confusion. So, let's bring clarity to this. At the highest level, we have artificial intelligence, and this is the broadest category. Artificial intelligence includes any system designed to perform tasks that would normally require human intelligence. Things like recognizing patterns, making decisions, and solving problems. Now, here is the important part. Not all AI learns from data. Some older systems were rule based, where humans explicitly wrote instructions for every situation. So, think of AI as the umbrella, and everything we have been discussing sits inside this larger space. And now, inside AI, we have machine learning, and this is where things start to connect directly to what we have just learned. Machine learning is a subset of AI, and it refers specifically to systems that learn from data instead of being programmed with rules. So, when we discussed maps predicting traffic, or recommendations, or spam filters, those are not just AI systems, they are machine learning systems, because they improve by learning patterns from data. They do not follow fixed instructions. And now, inside the machine learning, we have deep learning, and this is a more specialized category. Deep learning uses structures called as neural networks, and instead of learning simple patterns, it learns patterns within the patterns. Okay, let's make that concrete. In a basic system, you might detect simple features, but in deep learning, the first layer might detect edges in an image, and the next layer combines edges into shapes, and the next layer combines shapes into objects. So, the system builds understanding in layers from simple to complex, and that's why it's called deep, because there are multiple layers of processing. And now, connect this back to the real systems. Deep learning is what powers modern face recognition, speech recognition, and advanced language models. These are the problems where patterns are too complex to capture with simple methods. So, if we step back, the hierarchy becomes clear. Artificial intelligence. This is the broad field of intelligent systems. The machine learning, the systems that learn from data, and deep learning, a specific approach within the ML using layered neural networks. And here is the key insight. Every deep learning system is machine learning. Every machine learning system is AI. But not all AI is machine learning, because that distinction matters. Because when people say AI, they often actually mean machine learning or deep learning. And now you can separate those ideas very clearly. Okay, till now we have seen how learning evolved at each different stage. And the next step is to understand something more specific, because not all machine learning works the same way. Even though all of it is based on learning from data, the way that learning happens can be very different. For machine learning, there are three core approaches, and once you understand these, you'll start recognizing them in real systems. Now, let's start with the first one, supervised learning. This is the most straightforward way to train a system. You give it an input and the correct answer. So the system learns a mapping between the two. Take a concrete example. Imagine you have 10,000 images. Each one is labeled a cat or a dog. The system looks at these examples and learns patterns that connect image to the label. And over time, it figures out what makes something look like a cat and what makes something look like a dog. So when you give it a new image, it automatically predicts the correct label. Now, notice what made this possible. The labels that the user provided. Someone had to provide the correct answers, and that's why it's called supervised, because the system is being guided with known outcomes. And this approach is widely used in real systems like spam detection, medical diagnosis, credit scoring, image classification. Now, let's move to the second approach, unsupervised learning. Here, this setup changes completely. You still give the system the data, but you don't give it any answers. No labels, no correct output. So, what does the system do? It tries to find structure on its own. Again, let's take an example. Customer purchase data. You have information like what people buy, how often they buy, and how much they spend. But you don't tell the system these are premium customers or these are casual buyers. Instead, the system analyzes patterns and groups users based on similarities. It might discover that frequent buyers, the discount driven buyers, or occasional shoppers. These groupings were not predefined, they emerge from the data. And this technique is powerful because it can reveal patterns you didn't even think to look for. And that's why it's used in customer segmentation, anomaly detection, and recommendation systems. And now the third approach, reinforcement learning. And this one is very different. Here, the system is not just observing data, it is interacting with an environment. Here, it takes actions, and based on those actions, it receives feedback. That feedback comes in two forms, either rewards or penalties. And over time, it learns which actions lead to better outcomes. Think of it like learning a game. For example, chess. The system makes a move. If that move eventually leads to a winning, it is rewarded. But if the move leads to losing, it is penalized. And by repeating this process millions of times, it learns strategies that maximize the reward. Now, notice the key difference here. There are no direct labels and there is no fixed dataset with answers. Instead, learning happens through trial, feedback, adjustment, and repeat. And this approach is used in game AI, robotics, self driving systems, and real time decision systems. Now, if you step back and compare all three, supervised learning learns from labeled examples, unsupervised learning finds patterns without those labels, and reinforcement learning learns through interaction and feedback. Same goal, but different ways of learning from data. The AI learning cycle. Let's visualize that same process in a slightly different way, because sometimes seeing the cycle as a flow makes it easier to understand what's actually happening. Now, let's start at the top. Input examples. This is where everything begins. The system is given data to work with, not instructions, not rules. It is just given examples. These examples could be images, text, user actions, or sensor data. At this stage, nothing intelligent is happening yet. The system is simply being exposed to the information. And now, once it has enough examples, it moves to the next step, finding patterns. And this is where the system starts to detect relationships. For example, certain words tend to follow others, certain visual shapes tend to appear together, and certain behaviors lead to certain outcomes. It's not labeling them in human terms, it's identifying statistical relationships. And this is the core of learning, recognizing structure in data. And once the patterns are identified, the system uses them to make predictions, and then it adjusts itself. And this is the adjust model step. Based on how accurate its predictions are, it tweaks its internal parameters. Think of it like calibration, small adjustments that gradually improve the performance. If it predicts incorrectly, it shifts entirely. And if it predicts correctly, it reinforces that direction. And now, after adjustment, you get better output. The system's predictions become more accurate, more consistent, and more aligned with the real patterns. And this is the visible improvement, the part users actually experience. But the process does not stop there. It loops and it repeats the cycle. When new data comes in, new patterns are found and further adjustments are made. And with each cycle, the system refines itself. And now, the important thing to notice here is this: there is no final done state. The learning is continuous and it happens as long as new data comes in. The cycle can continue, and that's what allows these systems to adapt over time, not by being reprogrammed, but by continuously learning from new information. This stage represents a shift from rule-based systems to learning-based systems. Instead of manually writing rules, the system learns patterns from data. And this is the phase where machines begin to learn from examples. The focus moves from human written logic to data-driven learning. Now, instead of programming rules step by step, the system is given many examples, and from these examples, it identifies patterns on its own. For example, if you show a system thousands of emails labeled as spam or not spam, it learns patterns that distinguish between them. No one explicitly writes rules like if email contains X word, then mark it as spam. The system figures those patterns automatically. And this approach worked especially well in structured and repeatable environments. For example, in fraud detection, the system learns patterns of normal spending behavior. When something unusual happens, it flags it as potential fraud. You can also take spam filtering. By learning from millions of labeled emails, the system identifies patterns in spam messages. You can also see this in recommendation engines. Platforms suggest products, videos, or content based on patterns in user behavior. The machine learning performs best when data is organized. Numerical values, categories, tabular data. For example, predicting loan approval based on income and credit score, classifying customers into segments. These problems have clear inputs and outputs, making the pattern detection easier. Now, let's talk about the training data. It refers to the examples given to the system for learning. These examples form the foundation of the model. For instance, past transactions for fraud detection, or labeled emails for spam filtering, or we can use user activity for recommendations. This system uses this data to learn relationships and patterns. The quality of this data directly affects the system. If the data is accurate and diverse, the system performs well. If the data is biased, incomplete, or incorrect, the system will reflect those issues. Now, let's talk about AlexNet. It was introduced in a competition, and this competition was for large-scale image recognition used to evaluate AI systems. The goal was straightforward: determine whether a machine can correctly identify objects in images. However, the difficulty lies in how machines see images. An image is not a cat or a car to a computer. It is just a grid of numbers or the pixel values. And to solve this, models were trained on millions of labeled images and thousands of object categories. These competitions became important because they provided a common benchmark. The progress could be measured objectively, and improvements were typically small and gradual. For example, a system is shown an image. It must predict labels like dog, bicycle, or a building. So in 2012, AlexNet entered this competition and produced a result that was significantly better than all previous systems. The key aspects included: the error rate dropped sharply compared to previous years. The improvement was large enough to stand out immediately, and it was not a minor optimization. It was a clear leap forward. Let's understand what made this possible. It became possible due to the use of deep neural networks, training on large datasets, and use of GPUs for faster computation. And this result challenged existing assumptions. Earlier methods relied heavily on manual feature design, but AlexNet showed that models could learn features automatically from data. And following this result, the AI research community shifted direction. Before AlexNet, multiple competing approaches were being explored. Neural networks were not widely trusted for large-scale problems. After AlexNet, deep learning became the dominant approach. Research labs adopted neural networks rapidly. Investment and focus moved toward data-driven methods. And this change happened quickly because the improvement was clear and measurable. It demonstrated a more effective way to build AI systems. And this movement represents a transition in how AI problems were approached, from manually designing features to learning directly from data, from incremental progress to breakthrough driven progress. The AlexNet is widely considered the starting point of the modern AI era because it established deep learning as the most effective paradigm for solving complex problems. Now, let's talk about AlphaGo. Go is fundamentally different from games like chess. The key challenge was the number of possible board positions is extremely large. It is far greater than what brute force computation can handle. In chess, AI could calculate many moves ahead. The problem was complex but still manageable. Whereas in Go, the number of possibilities is astronomically high. You cannot simply calculate everything. The success depends heavily on intuition. And pattern recognition. And because of this, experts believed Go would remain out of reach for AI for decades. It was considered too complex, too abstract, and too dependent on human like intuition. So in 2016, DeepMind's AlphaGo defeated Lee Sedol, one of the world's best Go players. And this was significant because it was not expected to happen so soon. It was not a narrow win either, it was a decisive win. It proved AI could handle problems previously thought impossible. AlphaGo combined deep neural networks with reinforcement learning. It learned patterns from data instead of relying only on rules, and it improved by playing against itself. And this made AlphaGo different. Now, the AI was no longer limited to structured or rule based problems. It could handle intuition driven tasks. This movement demonstrated a major shift from solving predictable problems to handling complex and uncertain environments. It showed that AI could learn strategies, develop intuition like behavior, and perform at superhuman levels in high complex domains. The significance was not just winning a game, it was proving a new level of capability in AI. Now, instead of keeping this theoretical, let's ground this in something real. Because it's one thing to say AI is good at pattern recognition at scale, but it's completely different when you see what that actually means in a high stake situation. There's a study mentioned here, a landmark study published in Nature. What they did was very straightforward in design. They took an AI system and compared it directly with experienced radiologists for detecting breast cancer from mammography scans. Now, just to be clear, this is not a trivial task. This is the kind of work where missing a case can be critical, and over detecting can also create serious consequences. So, accuracy matters a lot here. Now, the results. The system showed fewer false positives and fewer false negatives. And in controlled conditions, it actually outperformed experienced specialists. And at this point, it's very easy to jump to a conclusion like AI is better than humans. But that's not the right way to interpret this. The more important question is, why did it perform better in this specific situation? And the answer is right there. The system was trained on more images than any human specialist could realistically review in an entire career. Think about how a human builds expertise. Over time, years of education, thousands of cases, and gradual pattern recognition. Now, compare that with AI system. It has already been exposed to hundreds of thousands or sometimes millions of scans. So when it analyzes a new image, it's not reasoning through it step by step. It's matching patterns against a very large history of similar patterns. And this connects directly to what we discussed earlier. This is not about intelligence. It's about volume of exposure and consistency of processing. The system doesn't get tired, lose attention, or become inconsistent. It applies the same level of analysis to every single case. Now, there's one more important part here, the implication. When this kind of pattern recognition at scale is applied to something like medical diagnosis, it can actually improve outcomes. In some cases, it can help detect issues earlier and potentially save lives. But, and this is important, this works well because the problem fits AI strength, large amounts of data, repeated patterns, and structured input. So the takeaway is not AI replaces doctors. The real takeaway is AI becomes extremely powerful when applied to problems where pattern recognition at scale matters. And once you see that clearly, you also start to see the boundary because Outside of this kind of problem, the same system may not perform the same way. And that's exactly where we go next. What happens when the problem is not driven by patterns at scale? Take that same idea and bring it back to everyday systems. This is about something much more fundamental: consistency at scale. Humans don't operate continuously. We get tired, we lose focus, and we make mistakes, especially over time. But AI systems don't have that limitation. They don't have bad days. A system can process a query at 9 a.m. and another query at 3 a.m. All of this with same accuracy, same logic, and same response quality. No fatigue, no drop in performance, and no end of shift errors. And that's the first major difference: consistency over time. Now, think about repetition. If you ask a human to do the same task 10,000 times, attention drops. Small variations creep in and errors accumulate. But AI systems behave differently. The first task and the 10,000 tasks are executed the same way. No shortcuts, no boredom, and no gradual decline. As long as the task is clearly defined and the task is within scope, the output remains stable. And that's the second idea: no performance drift. Now, let's talk about scale. A human can handle one task at a time, maybe a few with effort, but AI systems are built differently. The same model can handle millions of requests simultaneously. For example, millions of people asking questions, millions of transactions being checked, and millions of recommendations being generated, all happening at the same time with consistent behavior across all of them. No coordination overhead, no communication delays, and no scaling bottleneck like human teams. And that's the third idea: massive parallel execution. The reality behind this power. Now, this sounds like a perfect system, but there is an important detail. This consistency is both a strength and a limitation because AI does not understand context the way humans do. It does not know when a situation has changed, it doesn't recognize when rules should be broken, and it does not decide when to stop on its own. It simply continues, applying the same learned patterns again and again. So, the key takeaway is AI is incredibly powerful at consistent execution, but it is weak at judgment, adaptation, or awareness. And understanding that difference is what allows you to use AI effectively. And once you understand that AI fails in predictable ways, the next question is, what is it actually doing under the hood? Because if you misunderstand this, you will overtrust it. Now, let's see what AI actually does. At its core, AI is doing something very specific. It is predicting what comes next in a pattern. It is not thinking, it is not reasoning in the human sense, and it is not understanding truth. It takes the input you give, the patterns it has seen before, and generates the most likely next response. And that is the mechanism. For example, if you ask, explain gravity in simple terms, the model does not actually understand gravity. It has seen many explanations of gravity. It recognizes patterns such as simplified explanations, common analogies, and familiar structures, and it generates a response that fits those patterns. So, when the answer is good, it is because similar patterns existed in its training, not because it independently understands the concept. Now, consider a student who has spent their entire life inside a library. They have read thousands of books, countless explanations, and detailed descriptions of the world, but they have never stepped outside. If you ask them something directly from those books, they will give excellent answers. But if you ask them something slightly new, they will still respond, but now they are constructing an answer by combining patterns from what they have read. The response will sound convincing. It may even sound correct, but it can also be completely wrong because their knowledge is not grounded in real world experience. And this is how AI behaves. The key limitation is this: AI does not know why something is true, it only knows what kind of answer typically follows a question like this. And this is why it can explain complex topics clearly, generate code, and summarize information. And at the same time, it can make confident mistakes, produce incorrect facts, and hallucinate details, not randomly, but because it is always predicting and not verifying. Hallucination is not a separate issue, it is a direct result of how the system works. When the model does not have a strong pattern, it does not stop. It generates the closest possible answer. For example, if you ask about a niche or unfamiliar topic, it may invent details, it may create references, and it can fill gaps with plausible sounding content. And it will present this confidently, not because it is trying to mislead, but because it cannot distinguish between what is grounded in data and what is generated from patterns. AI is a prediction system, not an understanding system. It is extremely powerful at recognizing patterns, generating structured responses, and producing human like language. But it does not have true comprehension, grounded reasoning, and awareness of correctness. And once you understand this, you stop asking whether AI understands like a human and start evaluating whether the response is based on reliable patterns. And that shift is what allows you to use AI effectively. And once you understand that AI is predicting patterns and not understanding the truth, this leads directly to one of its most important failure modes, not just being wrong, but being confidently wrong. And this is what makes hallucination dangerous. In most systems we use, there are signals when something is wrong. A calculator shows an error, a program crashes, a human hesitates or says, I am not sure. But AI does not behave like that. It produces responses that are fluent, structured, and confident whether the answer is completely correct or completely fabricated. And there is no built in signal that tells you this might be wrong. For example, if you ask for an obscure fact, the response will sound just as confident as a well known fact. You cannot hear the difference, and that is the first problem. No visible uncertainty. Plausible, not true. Now, why does this happen? Because the system is optimized to generate answers that look correct, not necessarily answers that are correct. Hallucinations are not random mistakes. They are structured, they follow patterns of what a correct answer should look like. For example, if you ask to cite a source, the model might generate a realistic looking paper title, a plausible author name, and a believable explanation. Everything fits the pattern of a real answer, but the source may not exist. So the output is coherent, convincing, and false. So the key idea is AI produces plausibility, not guaranteed truth. Now combine these two ideas, no uncertainty signal and high plausibility. You get a system that can confidently point in the wrong direction, like a compass that is slightly off but never tells you it is off. And the problem is not just the error. Errors are normal. The problem is the confidence attached to the error, because confidence leads to trust and trust leads to unverified use. For example, trusting a generated medical explanation without checking, or using incorrect code in production, or relying on fabricated references in research. In each case, the issue is not that the model made a mistake, it is that the mistake looked reliable. And hallucination is not a rare bug, it is a natural consequence of how AI works. A system designed to generate fluent pattern based responses will sometimes generate fluent pattern based errors, and it will present them with the same confidence. And that is why verification is not optional. It is the minimum requirement for using AI responsibly. You do not evaluate AI outputs based on how confident they sound. You evaluate them based on whether they can be checked and confirmed. And that shift from trusting confidence to verifying correctness is essential. And once you understand that AI can be confidently wrong, the next question becomes, what happens when people trust it anyway? Because this is not just a technical issue, it has real world consequences. Now, let's look at a real case. A passenger interacted with Air Canada's chatbot. He asked about a fare, a discounted ticket offered in certain situations. The chatbot told him he could apply for the discount after completing his travel. And that answer sounded clear. It sounded official, it sounded trustworthy, so the passenger followed it. He booked the ticket, completed the trip, and then applied for the refund. But here is what actually happened. Air Canada's real policy required the bereavement discount to be applied before travel, not after. So the chatbot's answer was wrong, not slightly misleading, not ambiguous. It was factually incorrect about company's own rules, and this is important. The system did not hesitate. It did not say, please verify. It gave a direct, confident instruction that was totally wrong. This is exactly the kind of response users are most likely to trust. The case went to a tribunal. Air Canada argued that the chatbot was a separate tool and not a human agent. But the tribunal rejected that argument and they ruled the company is responsible for what its chatbot says. In other words, you cannot deploy an AI system and then deny accountability for its outputs. And this case establishes something much bigger than a refund dispute. It sets a precedent. AI is not just a tool, it is an extension of the organization using it. If it gives incorrect information, the responsibility does not disappear, it transfers to the company. Think about the implications: customer support, financial advice, healthcare interactions, legal guidance. In all these areas, a confident but incorrect response is not just inconvenient, it can be costly. And this connects directly to what we discussed earlier. AI does not understand policies, it generates responses based on patterns. So, even when it is answering about its own company, it can be still wrong. And when users trust that output, the consequences become real. So, deploying AI is not just a technical decision, it is a responsibility decision. If a system speaks on your behalf, you are accountable for what it says. And that is why verification matters, guardrails matters, and human oversight matters. Because once AI leaves the lab and enters the real world, its mistakes are no longer theoretical. They are legal, financial, and human. So far, we have understood how AI works, where it succeeds, and more importantly, where it can fail. Now, the focus shifts to something practical. How do you actually use AI reliably in real world situations? Because the difference between useful AI and risky AI is not the tool itself, it is how you use it. What follows are a set of habits that ensure you get value from AI without falling into its common traps. The first and most important rule: do not treat AI output as a final answer. Treat it as a starting point. Even when an answer looks polished and confident, it can still contain errors. For example, if AI provides a medical recommendation, a legal interpretation, or a financial decision, acting on it immediately can be risky. Instead, cross check important claims, verify with trusted sources, confirm critical information independently. The higher the stakes, the stronger your verification should be. Next up, AI responds directly to how you ask. If your prompt is vague, the response will also be vague. For example, explain machine learning. It produces a general answer, but explain machine learning in simple terms with one real world example in 5 bullet points. Now, the system has clear direction, defined scope, and expected structure, and the output becomes significantly better. Clarity in input leads to clarity in output. Next, do not depend on a single response. If something feels incomplete, ask again from a different angle. You can rephrase the question, ask for examples, or request a simpler or more technical explanation. For instance, explain this simply. Now, explain it in technical terms, and later give a real world use case. If the answers remain consistent, the confidence increases. If they start to vary, it indicates uncertainty. And next, AI systems should not be treated as private or secure environments. Anything you input can be processed, stored, or logged. So avoid sharing passwords, financial details, personal records, confidential business data. For example, uploading internal documents or client data can expose information beyond its intended use. A practical rule is if the information is sensitive, do not enter it into an AI system. And next up, getting an answer is only part of the process. You must evaluate it before using it. Check for hallucinations. These include fabricated information. Check for outdated facts and check for logical inconsistencies. For example, AI may generate realistic looking but fake references. It can also generate incorrect statistics or answers that sound right but are wrong, and it will present all of them with confidence. So instead of asking, does this look correct? Ask, can I verify this independently? Because confidence does not guarantee accuracy, and accuracy requires validation. All of this comes down to one habit: verify first and then act, never the other way around. And this is what turns AI from a risky shortcut into a reliable tool. Which path is yours? And this is not about choosing what sounds more impressive, it's about choosing what aligns with your curiosity, your strengths, and your real world needs. Now, let's start with a simple question: are you more interested in how AI works or what AI can do for you? If your curiosity leans towards understanding models, exploring algorithms, and digging into systems, you are naturally leaning towards the builder mindset. If instead you are thinking, how can I use this in my work? Or how can this improve my decisions? You are leaning toward the applier mindset. Both are valid starting points, but they lead in different directions. Now, go one level deeper. Do you want to understand the internals, the architecture, training, optimization, or do you want to understand the outputs, how reliable they are, how to use them effectively? Builders focus on why the system behaves the way it does, whereas appliers focus on where the output is useful, correct, and safe to act on. And this distinction matters because it shapes what you learn, what skills you develop, and how you engage with AI day to day. And this is the most practical filter. Ask yourself honestly, what does my current role actually require from AI? If your role demands building tools, working with data pipelines, developing systems, then the builder path makes sense. But if your role involves decision making, interpreting information, applying knowledge in a domain, then the applier path is the right fit. And this is not about ambition, it's about alignment. Your answers to these questions will naturally point you toward one path. But one thing is critical: both paths are worthwhile. The goal is not to pick the more technical or more impressive route. The goal is to choose the path where you can contribute more meaningfully, act responsibly, and engage effectively. Because in the end, what matters is not which path you choose, but how consciously there is one habit that becomes essential no matter which path you are on. Whether you build AI or use it, this is the common discipline. Don't just use the output, interrogate the system behind it. And this habit is built around four critical questions. The first one: who built this? Before trusting any AI system, ask who created it, what data was it trained on, and what incentives shaped its design. Because every system reflects the priorities of its creators, the data it learned from, and the goals it was optimized for. For example, a model trained on internet data may inherit internet biases. A tool built by a company may prioritize engagement or profit. So, understanding the origin helps you understand what the system is likely to do and why. Next up, what can it get wrong? This is one of the most practical questions you can ask. Every AI system has failure modes. Ask yourself, where is this system likely to break? What kinds of mistakes does it make? And would I recognize those mistakes if they happen? If you cannot answer these questions, then you are not yet in a position to fully trust the output. And this is especially important because AI errors are often confident, fluent, and not clearly flagged. So, your job is not just to use AI but to anticipate its weaknesses. And next up, who is accountable? When something goes wrong, responsibility does not disappear. Ask who is accountable for this system: the developer, the company deploying it, or the person using it. The answer may not always be clear, but thinking about accountability helps you decide how much to trust the system, how much verification is needed, and when to rely on human judgment instead. If the consequences are high, your level of caution should increase. And lastly, whose values? Every AI system embeds values, not always explicitly, but through decisions like what data is included or excluded, what outputs are allowed or restricted, and what outcomes are optimized. So the key question becomes, whose perspective does this system reflect, and do those values align with mine or my context? Because AI is never neutral. It always carries assumptions about fairness, priorities, and acceptable outcomes. And understanding this helps you use AI more consciously and instead of treating it as an objective authority. And all four questions point to a single mindset. Do not treat AI as a black box. Instead, question it, understand it, and evaluate it before acting. Because whether you are building systems or using them in real life, this habit is what turns AI from a risk into a tool that you can actually trust. Treating it